So now I will move a little bit faster to persistent luminescence and afterglow. So persistent luminescence and afterglow, this is this part of the traps. So that means shallow traps and the trap between deep traps and shallow traps is called useful trap, for instance, for persistent luminescence. So a traps here with a signature in thermoluminescence around 300 Kelvin, that means room temperature, and you have persistent luminescence. So this is what we study in the research lab in Paris, and it's very important to have, for instance, material for medical imaging for different applications. This is, for instance, this kind of apparatus to control the tumor, for instance, or to control the metabolism. So this can see accumulation of tumor, for instance, by a PET scan, or this is to control the metabolism. This is the circulation and the good functionality, for instance, of your brain. This is a brain with a normal brain, with excitation of the brain. You are asking questions to this guy. This guy is normal. Just to try to ask difficult question. This is a guy doing some PhD examination, for instance. And this is a person with Alzheimer, and you see the irradiation, not irradiation, the circulation is prevented, is very bad. And even when there is stimulation, there is still some problem in Alzheimer part. So in the lab, we are working on this kind of material in pixels, which are inside the apparatus. And it's very important to control the quality. And in this case of position emission tomography, the key point is the persistent luminescence. We have to avoid the persistent luminescence. This is, for instance, very old image, the tomography with very old image. You see there is a very low, the images are not of very good quality, while this is a more recent image. And you see the quality are very good. You can clearly see some details. And between these two, there is an improvement of the apparatus. It's very clear. You have good apparatus. You can do some very good image. And when the apparatus has some persistent of afterglow, the images are blurred and very bad quality. So in the lab, we demonstrate that in this kind of material, LYSO doped with cerium, the origin of the trap was a type of oxygen vacancy, and we succeed to put dopant to limit and to decrease the afterglow. In that case, in the next generation sold by Philips, the apparatus have much less afterglow than the previous one. This was done also for X-ray tomography. It was exactly the same approach. And for the tomography, you have also to move very quickly either the X-ray source and the X-ray detector to do some tomography and to do some tomography within a few minutes, for instance. And the same, we use thermoluminescence. Here you can see the thermoluminescence curve. So you recognize the thermoluminescence glow curve around 300 Kelvin. This is the room temperature. And you see that when you decrease this thermoluminescence peak, there is no more afterglow. Here there is very low afterglow here. I will show you in 1 minute. And here there is a very strong afterglow. So this is the decrease of the afterglow when you are moving from one kind of material to another kind of material. So that was a recent patent that we got with Saint-Gobain for this kind of apparatus. So in some case, we need to enhance the afterglow. So I put this because we would like to have persistent luminescence on the good side. In the good side is here because, and in the bad side. So this is you can recognize here the female. That's I think this is the bad side because there is a cold and ice. Okay, I don't know why they put the female here, but you should tell me. And so we would like to put persistent luminescence on both sides and to enhance persistent luminescence. So I came here also, at Kyoto University. And you can see, for instance, this is amazing. This is a picture that I took for a small exhibit of Professor Tanabe. And there is no excitation here. The excitation was cut. This is a reflection of the lamp. You see that the lamp is there. And you can clearly see that there is still very high luminescence, clearly seen by the haze after several minutes. And this is a group. You can recognize most of the person here. And you can see that it's important to use this material to enhance persistent luminescence and to do some material with a lot of interest. So we can call that also optical battery, because in that case you can store in the battery the energy, and you can release the energy after several hours. So it's very interesting, for instance, for this kind of application, for the exit sign, or for lightning, or for different application, LED now, or something like that. So very important field, and I am pleased to see that here in this lab there is a lot of activities, very nice activity of this. So in Paris we try to use this activity, we try to look at this activity to do some optical imaging, to use at bioimaging with persistent luminescence. So if you look at the persistent luminescence and long-lasting phosphor, there is a lot of papers starting after the main publication about strontium aluminate, co-doped with europium and dysprosium, discovered here in Japan. And you see, but in vivo imaging, you see that 2014, there is already more publications than last year. And that means that at the end of the year, we will have maybe 2 times more publications than in 2013. So the field is really increasing very quickly. And I am pleased to see that several other labs are looking at this for application. So what's interesting is that we can do, I will only need 5 more minutes, and sorry for to be long, but we use the transparency of the body in the near-infrared range. So, and the way to do that is to use persistent luminescence. So you use the persistent luminescence to look a long time after the injection to the animal at the emission. So we call that time management, and we propose to use that to do some image of tumor and different applications. So of course, again, thermoluminescence is very important. I told you in the title that this is from thermoluminescence. So thermoluminescence is very important to analyze the traps and to try to look at the mechanism. So this is a mechanism we are pumping at 2 different wavelengths, for instance. So thermoluminescence, very efficient tool to do that. After, of course, you need to prepare the material. And in that case, this is nanomaterial. You need to prepare small size material in order to have a circulation within the body. So this is an example of this kind of material with PEG, for instance, with hydroxyl and with other functionalization with positive, negative, and neutral coating. And you see, this is what happened. This is the animals, and you have injection of the nanoparticle. Within a few minutes, in the case of positive and negative charge, the nanoparticles are directly trapped either in the lung or in the stomach here. If you put neutral nanoparticles, you can have circulation of the nanoparticles within several minutes, and it will stop at around 30 minutes, I guess. And you see, you increase the circulation. So this is what was done for the first publication, in fact, 6 years ago. And you can clearly see that in the PEG, this increase of the circulation because of the neutral charge of the nanoparticles. So what we did recently was to use this nanoparticle to localize tumors. So this will, you can see here, tumors localized with the use of the nanoparticle inside the small animal like this. So it was published recently this year by Thomas Maldini, for instance. We also look at the roll circulation and ischemia. This is a good example of the use of nanoparticles. This is a lever, and you can see this is the shape of the lever, and we cut the circulation of the liver of half of the liver. And we prevent the circulation of blood in this part of the liver. And then we block the circulation, and then we block the circulation to put some pressure, by some pressure. And then again, we look at the recirculation. That can happen, for instance, if you have an accident you are cycling and you have an accident, and suddenly you have a very bad circulation of your legs, and you can check if the circulation is correctly what's happened with the circulation, and there is a recirculation. We call that ischemia and vascularization. So ischemia is when you cut the circulation, and vascularization again of some organ. And we saw that after 5 minutes, there is again, by this kind of nanoparticle, we can see that there is again the circulation. And this is, of course, due to we put injection of nanoparticle inside, and we follow the long-lasting persistent luminescence of this. We follow also administration of medicine, and you can see, for instance, 4 hours after the administration, what's happened to the medicine. This is, for instance, nanoparticle in water, and you see it is going here, and after 4 hours you can see the dispersion of the medicine, and you can see that after 1 day there is still the active medicine inside the body of the animal. And it was impossible to determine by other techniques. This is the classical way to determine if there is still some medicine, active medicine inside the body of the animal. So in that case, that means it's not necessary, for instance, to take a second pellet. Sometimes you have to take a pellet every 6 hours, every day, and so on. So in that case, you can look at the dispersion and the way that the medicine is dispersed inside the body, and follow the nanoparticle inside the animal. So that was 2 examples. Of course, I would like to finish by showing you that there is a lot of new work on these kind of things. That, for instance, in vivo and living cell using persistent luminescence, drug delivery and tumor targeting, multimodal persistent luminescence and NMR nanoparticle. There is also up conversion and persistent luminescence. So very different things made by this kind of persistent luminescence nanoprobe and bioimaging. There is, of course, only image of animals, because to go from animal to human is a different story. You need to have several years. So there is animal like a pork, small animal, a rabbit, and so on.